We just finished talking about free energy changes under standard conditions. Well, most things do not happen under standard conditions. If we look at liquid water evaporating into a gas state, delta G standard for that reaction is positive 8.59 kilojoules per mole. Is that spontaneous? No, it isn't. But if we spill water on the floor and wait, does it evaporate? It does. It is spontaneous. So what's going on here? Well, water spilled on the floor is not at standard states, right? The standard condition for that would be the partial pressure of water being 1 atmosphere. But that's not the case. Under ordinary conditions, the partial pressure of water in the air is much, much less than 1 atmosphere. And that's going to affect whether the process is spontaneous or not. So we need to calculate delta G under non-standard conditions. So delta G is the free energy of change. This is without the little zero here. Free energy change of a reaction under non-standard conditions. So it is related to the standard free energy change. That plus RT times the natural log of Q. Q is that reaction quotient that we learned about in previous chapters. T is the temperature. Again, we have to use kelvins here. And R is the ideal gas constant. There's 2 values of that we commonly use, but we want to use the one with joules here because we're talking about energy. We're not talking about volume and pressure like with gases. So 8.314 joules per mole Kelvin. If we've got reactions in the gas state, we're going to use the pressure quotient, and if it's an aqueous solution, we're going to use the concentration quotient. So for this equilibrium, this is our chemical equation here. If we calculate Q or K, remember K and Q are calculated exactly the same way. So the equilibrium constant with respect to pressure for this is the pressure of the products over the pressure of the reactants. So we've got the partial pressure of H2O divided by the reactant, but the reactant is a liquid. Remember, liquids and solids don't show up in equilibrium constant expressions because they don't change their concentrations. So Kp is just equal to the pressure of water, okay? So Q is calculated exactly the same way as K. It's just it doesn't have to be at equilibrium. Under standard conditions, what is the partial pressure of H2O? 1, right? Under standard conditions, Q is 1, and so then delta G will equal the standard free energy change. If we have a partial pressure of water that's less than 0, then, let's look at that. So delta G equals delta G 0 plus RT natural log of Q. Well, let's just say that Q is 0.5. What's the natural log of 0.5? Well, let's find out. Negative 0.693. So natural log of Q is negative. So that means that delta G is going to be smaller than the standard free energy change. Under standard conditions, Q is 1, and these are equal. But when the pressure is lower than 1 atmosphere, then delta G is less, and so the reaction will be spontaneous. Over here, if the pressure wait a minute, I did that wrong. When Q is smaller, it's going to reduce delta G. That doesn't necessarily mean it's going to be spontaneous there. But at the point where Q is equal to K, then that's where the delta G is equal to 0. And so below that, and that happens at 0.0313, below that, it will be, the evaporation will be spontaneous. Above that, the condensation of water will be spontaneous. I probably just should have stopped on that one a long time ago. Any questions? It was bad. Sorry about that. So 25 degrees Celsius, liquid water is in equilibrium with water vapor at a pressure of 0.0313. So let's calculate what delta G for this reaction is. Delta G equals the standard free energy change. That's given right here. We got 25.00. So we should use the 273.15. We're going to get 298.15. 298.15 Kelvin. Natural log of Q. Here, Q is 0.0313. Now again, we've got a kilojoule-joule thing going on here. So I'm just going to do what's easier right now. And write 10 to the 3 instead of kilo. So 8.5 times 10 to the 3 plus 8.314 times 298.15 times the natural log of 0.0313. Is anyone bothered that it didn't come out to be 0? It's supposed to be 0. Sig figs. So here we've got 8,590 joules, right? And then we are adding, what was that number? 8.314 times 298.15 times the natural log of 0.0313 plus negative 8,586.96941, and that's going to have 4 sig figs at the max because of this guy. So when we add those together, we're going to get 3.03, but where's the uncertain digit? It's in the tens place. Because this is uncertainty right there. So we should round this number to the nearest 10, which is 0. Is that disturbing? It bothers some people. It's okay. It's so small that given the precision of these other measurements, we can't really measure it. We can do the calculation, but we can't really measure it. It's so small. So at equilibrium, delta G for the reaction is 0, and the reaction is not spontaneous in either direction. And this is a general truth. At equilibrium, delta G equals 0. Well, let's think about that. At equilibrium, is there a net movement towards products or reactants? No. It's going in both directions, right? Because equilibrium, dynamic equilibrium is not static. There's forward reaction and reverse reaction, but they're happening at the same rate. But overall, nothing's happening. Delta G being 0 corresponds to nothing happening. It's not spontaneous forwards or backwards. So if we have other non-standard conditions, we just calculate Q and we stick it into the equation. And of course, generally it is non-standard conditions. So that was at equilibrium. Here we have on a dry day, 8.59. Okay, I can't remember that number. So delta G on a dry day is 8.59. I'm just going to do that right away. Times 10 to the third joules per mole. That's standard delta G plus RT. We're going to assume the same temperature. We got 8.314. I reversed those, sorry. Joules per mole Kelvin. Natural log of 5 times 10 to the minus 3. So, rounding to reasonable sig figs and converting into kilojoules, we get a negative delta G. On a dry day, water evaporates spontaneously at room temperature. Any questions? Another good exam question. So that one was pretty simple. Let's do one that's a little more complicated. Consider this reaction at 298 K. Calculate delta G under these conditions. So here we have a chemical reaction where we have things that are in the gas state, and then we have this one solid. We are given partial pressures for all these gases. We're going to use Kp or Qp to do this. And so we're going to calculate delta G, and then it's asking if it's more or less spontaneous at these conditions rather than standard conditions. So delta G for the reaction is equal to delta G0 for the reaction plus RT natural log of Q. So we need to be able to calculate Q. So if we look at this chemical equation, let's write the equilibrium constant expression for that. What are they doing out there? So Kp is going to be products over reactants. Do we include solids? No, we don't. This is a gas, and so that's going to be the partial pressure of water. And there's a 2 in front of it, so this is squared. And then this is divided by, just did not choose a very good place to do this. I'm going to move it. I'll put it up there, a little more room. And we're dividing by the reactants. So we've got the partial pressure of H2S, and that has a coefficient of 2, so this one also gets squared. And then SO2 is just a coefficient of 1, so that's just the partial pressure of SO2. So we haven't done Kp for a long time. We did that at the beginning of chapter 16, and then we kind of ignored it. It's doing exactly the same thing we did with molarities, just with partial pressures. So that's the expression for Kp. What we need is Qp. So Qp, it's the same equation, but instead of equilibrium values, it's whatever we actually have. So we're going to take these numbers and plug them into that equation. So the pressure of H2O is 0.0100, and that's going to be squared. Divided by H2S, 2.00, also squared, and the SO2, 1.50. So Q is 1.67 times 10 to the minus 5. Now that I know that, I can do this calculation. We're given delta G for the reaction, minus 102 kilojoules, plus R, 8.314 joules per mole Kelvin, times the temperature. Here it just says 298. I'm okay with you putting 298.15 if you want, but I'm just going to go with 298K. And then the natural log of Q that we just calculated. 1.67 times 10 to the minus 5. Always write your units and look at them. Here we've got kilojoules and joules again. And so I'm just going to replace the K with what it means, times 10 to the 3. So I've got negative 102 times 10 to the 3 plus 8.314 times 298 times the natural log of 1.67 times 10 to the minus 5. What a ridiculous number. Anybody else get that number? Or something kind of close to it? I made a mistake again. I multiplied instead of adding. I thought that looked pretty weird. So let me fix what I did. Put a plus in there. There. Minus 129,253.5443. Still kind of a ridiculous number, but not as ridiculous. I got that first number by multiplying here instead of adding, so don't do that. And this is going to be in joules per mole. I forgot the per mole here. So this obviously should be in kilojoules. So move the decimal over and call this negative 129 point, oh, probably 129 is good, kilojoules per mole. Is it more or less spontaneous here than there? It's more, because this is more negative. Any questions? Negative 197. Okay, I probably did something wrong. Anybody else get 129? 298 to 1.5.01. I remember that number from yesterday. It could be that the book is wrong. So I really, really hate it when the book is wrong, because the book is supposed to be right. You do it and you do it and you're like, it's not matching up, and then you just like torture yourself, right? And then you find out that the book was wrong. So this is slide 81, so I need to remember to check this one and fix that. Yeah, because 197 is not the same as 129. It is still more spontaneous, so that's a little suspect as of right now.